Graphing a linear inequality is almost the same as graphing a line. The difference is you are shading a whole region, not just drawing a path. If you learn 2 visual rules and 1 algebra warning, these questions become very predictable on test day. Start by graphing the boundary line you would use if the inequality were an equation. That line splits the plane into 2 half-planes. If the inequality is strict, greater than or less than with no equal sign, draw a dashed line to show the boundary is not included. If you see greater than or equal to or less than or equal to, use a solid line because points on the line can be solutions. Then shade the side that makes the inequality true. For y greater than a linear expression, shade above the line in the usual xy plane orientation. If y is not isolated, you may rearrange first, but watch sign flips when you multiply or divide by a negative number. Example 1. Graph y is greater than 2x plus 1. Begin with the boundary d equals 2x plus 1. Strict inequality, so make the boundary dashed. That communicates the points on the line itself are not solutions of y greater than 2x plus 1. Shade above the dashed line, because y must be larger than the expression on the right for points in the region. Quick verification. Pick a test point that is not on the boundary, because the boundary is exactly where equality would hold. So try 0, 0. Is 0 greater than 2 times 0 plus 1? That simplifies to 0 greater than 1, which is false, so the origin is not in the shaded region. Example 2, a system. Each inequality gives a half plane. The solution set is where they overlap, if they overlap at all. Picture one region below y equals negative x plus 5 and another region above that y equals 1/2 x plus 1, depending on the inequalities you are given. Boundary lines can be solid or dashed independently for each inequality, depending on whether equality is allowed in that line's inequality. On the ST, you often shade the overlap on the figure they provide. The key is consistency. Every inequality must be satisfied at the same time. Example 3, integer points. Sometimes the question asks, how many ordered pairs of integers lie in the solution region, including boundaries if allowed? After you graph the region, list small integer coordinates and test them in every inequality. Do not assume a corner point is allowed unless the line is solid. If a point fails even one inequality, it is outside the feasible set. That is the same logic as testing answer choices. When the SAT caps the grid, list only integers in the window they drew, and remember that endpoints depend on solid versus dashed boundaries. Common mistake, you multiply or divide both sides of an inequality by a negative number, and you forget to flip the inequality symbol. For example, negative 2x is greater than 6. Dividing by negative 2 gives x less than negative 3, not x greater than negative 3. This shows up when you rearrange linear inequalities before graphing. Track negatives like they are precious. SAE pro tip. When you're unsure which side to shade, plug in a test point that's not on the boundary, often 0, 0 if it is allowed. If the inequality is true at your test point, shade that side. If it is false, shade the opposite side. This beats memorizing special cases. Recap. First, draw the boundary line, dashed or solid, matching strict or inclusive inequalities. Second, shade above or below, depending on whether y is greater or less than the expression, or rewrite into that form first. Third, remember the sign flip anytime you multiply or divide by a negative while isolating x or y. Fourth, for systems and integer counting, test points methodically so you do not miss a boundary case. Practice more on NovaMaths.